So, session is start, sir.
Hello and welcome to this second live session of the course GPU Architectures and Programming as is offered by NPTEL here. So myself, Professor Shoumujit De. So I will be online for the next half an hour or more than that, maybe 1 hour. So for any kind of queries that you may have, so we are tracking the queries. If you can post them either in the live chat or the interface provided to you, we'll be here to answer them. So before getting into that, I am just browsing through the forum that what are the different kind of issues that students may have been facing in the last 1 month or so period. So in this period, I think there has been coverage on memory access coalescing related GPU programming issues, and also there has been significant coverage on different kind of reduction techniques, right? So I see that there had been some queries on how reduction kernels are launched multiple times. So if you understand that when we give you an example of how a reduction kernel is working, we are assuming that there is a block of CUDA threads, right? So and they are doing the reduction on that. So that would mean that if you have a very big array, the reduction kernel needs to be called multiple times from a host program to do the reductions in parallel on different parts of the array, and finally you should be able to combine them and get it reduced to one single value, right? So that is the overall trick to do the kernel reduction. And I believe in course of these discussions that we did in the forum, we have also provided you suitable pointers to how to write a host program that will actually call such reduction kernels multiple times and give you the final reduction. Okay. Now, I have also seen there have been queries regarding modulo 2 operations, which have been, so there was this reduction optimization, which we did, right? So let me just go through that once. So if you refer to our reduction optimizations of the basic type, the first reduction kernel. So we opined there that first of all you have if condition inside a for loop, so that creates a lot of divergence, and the thread ID is being moduloed with a twice of s, right? So so that would be taking significant time. And so what we did was, as first of the first optimization on the base variant of the reduction kernel, we created another loop which would not have such an if condition, and there would be no modulo. Instead, a suitable index was calculated by multiplying 2 times the loop iterator value times the thread ID, and using that we are trying to access the suitable locations in the reduction array. Now the question is that why do we consider this more percentile operation as complex? The answer would be that, well, had it been a single percentile operation with a constant value, that could have been optimized. But in this case, as you can see, there is percentile 2s, and this iterator value s is continuously changing. So we do not have any direct operand for percentile implementation, right? I mean, it's not that you have something like that. So this would require some compiler code to be generated and executed, and that may take significant time. And rather than that, if we are able to do what we did in the next optimization, which is just compute twice of the thread ID times the S index, and just use that to get to the index for the corresponding array, that is going to be a definitely much faster operation. There was also a question like how division and multiplication operations are implemented in GPU. Well, the GPU ALU design will not vary too much from a CPU ALU design. As we know from our background in switching theory, there are well-known optimized algorithms for division and multiplication, both floating point and integers, to be done in hardware. and they typically get implemented. What I'm trying to say is there is no special optimization on how to implement division and multiplication inside a GPU vis-a-vis a CPU. That is not really there. Now, there was another question regarding parallel prefix sum, which I found, and that why I understand it will not work in single invocation of the kernel, but I am of the opinion that it may work in multiple repeated invocations. Well, if you see our in-place example of parallel prefix sum will still not work because different verbs that will be executing, they will be interfering, right? Because they are trying to write some intermediate results, and verbs of different blocks, they will not be synced up and they would be interfering, and that would cause to that would kind of create inconsistencies in the prefix sums intermediate values which are computed. And that's precisely why you use that non-in-place version which we show in the later examples. So apart from these, I do not see too many queries. So we'll like to wait here. If there are any more queries for the time being. I hope you are able to successfully carry out our assignments, because when I monitor our discussion forum, we do not see too many queries regarding problems that have been created apart from what we just discussed, right? So these are the typical issues that have been discussed, like issue with in-place parallel prefix, modulo 2 operation, code for reduction operations, which we have already provided to you, and these are the primary things that I can see in the forum. Not many other queries. So that's all. Maybe we'll wait for some time for you to come up with a few interesting questions if there are any. So while we wait, I would also like to point out a few interesting things that I hope you have gone through the reduction kernels slides, and you have studied all the different reductions that we have discussed, because they kind of really bring out the different facilities that are offered by GPU as a parallel computing hardware. For example, if you look into the further reduction operations that we talk about, we have methods which kind of alleviate the issues due to shared memory bank conflicts. So I think before this, the only place where you may have been facing shared memory was where we are able to accelerate matrix multiplication and matrix vector multiplication kind of operations by making suitable use of tiles in the shared memory. But that was also not a place where we we suffered from shared memory bank conflicts, and this issue was created in reduction operations. And if you see the further reduction optimizations like reduction optimization 3 and further, we are trying to optimize the code in such a way that this kind of bank conflicts go down. And specifically, if you look at the optimization that we do a down counting loop. Initially, we have higher stride values, and eventually we go for lower stride values. That is something that really helped. Okay, there is a question here from Prashant. In case of divergence, is the behavior of threads in warp and block different? Not really sure what you mean. So in case of divergence is a warp level phenomenon. So that would mean inside a warp, you have a set of threads. Now, suppose you have a branch condition and the warp is executing that branch condition. In case some of the threads in that warp satisfy that condition and some of the threads do not satisfy the condition, that is when you have a divergence. If all the threads satisfy the condition, then actually there is no divergence. So either all the threads will go to the branch taken part, or all the threads will go to the branch not taken part. There won't be any divergence, right? So, okay, if condition is saying false for all threads in a warp, then you really don't have any divergence, because the threads are kind of still executing together, right? I mean, they just they just still continue executing together in that suitable path. And if you are talking about blocks, as I am saying, it's still a warp level phenomenon. So you have a warp, you have a block. Inside a block, you have a set of warps that are being formed by the warp scheduler, right? Now those warps may or may not diverge depending on what condition you have given, right? And the same thing is going to happen for all other blocks also, which may be executing in that same SM or the other SMs. So it's basically a warp level phenomenon. So I really don't get what you mean by for block. For a block, like I said, that it will be not for blocks. It's basically at a warp level. Is this clear, Prashant? If you may reply. Yeah, so if the condition is false for all threads in a block, like you mean, then also that warp analogy will continue, right? Because that would mean in the block, whatever warps are getting formed, none of the warps are going to be satisfying that if condition, or maybe satisfying, all of them are satisfying the if condition. So again, there is no divergence. I mean, it's very clear, right? I mean, if it is at a warp level, then the same analogy will be going to the block level, right? Every block finally gets down to a set of warps, right? Now, it all depends on what is the branch condition. If the branch condition is a function of the thread ID, then you may or may not have divergence. If the branch condition doesn't have any function of thread ID, then you don't have any divergence, right? Now, of course, your if your I mean, so it is also dependent on what is the condition given for the branch, right? Suppose you have a condition which is conditional on the block ID. Let us try to think like this. So you are saying condition is not false for a block. So let us try to take an example. Suppose you have a if condition which is conditioned over the block ID and not really the thread IDs, right? So then that would mean that the block entirely will either satisfy the condition or not satisfy the condition. But in both cases, you don't have any divergence, because if it's not dependent on the thread IDs inside the block, then the entire block either goes this way or the other way. As long as your warps do not split, there is no divergence. It is as simple as that. If you remember this, I think you are done. Okay, let us say we have 512 threads and condition is local thread ID greater than 256. Well, so you can see what it will mean, right? So local thread ID greater than 256 would mean every thread ID greater than 256, the warps which are inside those thread IDs, they will go one way, right? And all the warps which are having the local thread ID less than 256 will go no other way, right? Now, since 256 will be just a multiply, it's basically it fully divide. I mean the warp size can divide 256, right? It's a factor of 256. That means in no warp you will have thread IDs, so that some of them satisfy the condition and some of them will not satisfy the condition. If you make it, let's say 255, sorry, 0 to 255, these are the thread IDs. The warps which are being made with these thread IDs, they are not satisfying the condition, right? So they will be going one way. So there is no divergence. The warps do not break. It will, I mean, you have divergence only when the warp breaks. And again, your if condition doesn't have anything to do with blocks, so it doesn't really depend on what is the block ID, right? Because you are talking about local thread IDs. Okay, I think now I mean we have given enough examples to tell you that it is not dependent on the block ID unless that is what the condition demands, and a divergence really means a warp has to get split. None of the situations you are giving, the warp will get split, so there won't be any divergence. So I think if you do some more programming assignments where you are playing with these things, it will be much more clear. So try to generate if conditions where you have thread IDs, block IDs, and all these things together, and try to run the programs. I mean, of course, you have to load the if and else parts with significant amount of code, so that when you run the programs and profile the programs with NVIDIA profilers and all that, you should be able to actually observe that well there is any difference happening or not. Try with various kinds of if else conditions. You condition them with block IDs, you condition them with thread IDs. I think that hands-on will give you a much better idea. But the rule is very simple: unless a warp breaks, unless a warp splits across the if condition, there is no divergence. It will happen whenever your warp will split across the if condition. So that was something important to talk about. One needs to really understand divergence and all that. And if you look into the further optimizations on reduction that we did, there is also another very important thing that you have to understand, that whatever optimizations you do, like shared memory optimizations and all that, at the end of the in the GPU, at least for kernels where the data transfer load is more than the compute load, to get more parallelism, it is very important to get some part thread activity, right? So that is why you will see that when we talk about the latter optimizations reduction, we are trying to increase the part thread activity, making threads to load two values from the memory and do the first addition on the shared memory itself. So all we are doing is, these are very kind of, I mean, they don't look very smart optimizations, right? There is not much of technique involved, but what it does is it is increasing our part thread activity to really make sense in terms of performance. So that is something important to remember there. Okay, so there is a on OpenCL APIs. Do you need to recall OpenCL APIs in the final exam? I would say whatever we are discussing, right, in the regarding OpenCL in our slides, right, that much you should really need to look into. But of course, I mean, the questions will not ask you like write an OpenCL call with everything you have to remember, recall, and write there. It would maybe of a filling the blanks type or something. So essentially, that would mean that you need to remember in the call what kind of arguments go where, what is the meaning of the arguments, because that is something anyway you need to know to learn OpenCL. And by the way, that is also a very useful programming language apart from CUDA, because suppose tomorrow you are interested in high performance programming for embedded platforms, let's say mobile phones and others, right? So there several derivative languages are OpenCL. For example, SYCL, DPC++. So these are frameworks, heterogeneous programming frameworks that have come up, C++ based frameworks, which are used for embedded GPU programming in several domains. For example, mobile platforms, right? So, I mean, don't get frightened by OpenCL APIs. Well, I understand there are a lot of arguments and all that, but you just need to understand and recall during exams what is the meaning of each of the arguments. You won't get a question where you are just asked to, you are given an ND-range kernel kind of command, and you are asked to fill up all the arguments. That kind of question never comes, right? I mean, we try to ask you questions where we will just test whether you recall what are the important things that needs to be passed to the function, and not all of them you have to write, maybe some blanks or something. Okay, if there is anybody else, you may also post your questions in the live chat. We are here for a couple of minutes more. Okay, so there is another question from Prashant. NVIDIA GPU programmed with CUDA and OpenCL, how would be difference in performance? Well, uh, so like NVIDIA GPUs and the CUDA programming language, both are from NVIDIA, the company itself, right? So definitely the lower level drivers that NVIDIA provide, they provide you the lower level drivers for the CUDA programming language, and they also provide you the lower level drivers for the OpenCL programming language, at least in the desktop GPUs. So what happens is that, of course, since for CUDA, the vendor is common for both the language as well as the hardware, those drivers are kind of better to say the runtime system. The CUDA runtime system executes much more efficiently in the NVIDIA hardwares, because I mean they really know what are the internal optimizations in the hardware. Whereas of course NVIDIA OpenCL is a kind of a open standard, and these are the vendors who conform to the standard, and that's why they provide lower level OpenCL implementations to support the OpenCL programming language. But definitely for most programs, most intensive programs, if you are writing a CUDA code and an OpenCL code for an NVIDIA platform, you are more likely to get better performance for the CUDA code. But that's for only NVIDIA platforms, not maybe for other platforms. For example, it may not hold, I mean, for other platforms, because OpenCL code will execute seamlessly in most other platforms which also support OpenCL, and that list is a big one, right? So if there are any other questions for anybody, please post in the forum. Maybe we are here for another couple of minutes. Till now, there is no other query. Okay, maybe if there are no more questions, we will end the session. Okay, thank you. I think there have been several good questions, and now maybe we'll end it. Thank you. ये क्या जश्न? Okay, bye.